Example three's rational expression is e to the x minus 1 over 2 e to the 2x minus 1. So with all limits, I'm just going to plug in that actual limit value of 0 and see what happens. So I get e to the 0 minus 1 in the numerator, and then e to the 2 times 0 is 0 minus 1 in the denominator. When I evaluate that, e to the 0 is 1, so 1 minus 1 is 0. In the denominator, I get 1 minus 1, which is 0. Now, this is problematic because 0 over 0 doesn't tell me anything. Okay, it could actually equal anything. It could be 0, it could be infinity, it could be anything in between. So we have to be able to evaluate this, we need some other strategy. And what we could do is we can try to algebraically simplify this to see if we can get rid of the divide by 0. So to do this then, if I recognize that the denominator really is a quadratic and it's a difference of squares. Okay, so it's actually e to the x squared minus 1. So I can rewrite this as e to the x minus 1 in the numerator, and in the denominator it becomes e to the x plus 1, e to the x minus 1. And so when e to the x is equal to 0, I have e to the x, e to the 0 minus 1. There's a 0 in the numerator. And I also have e to the x minus 1, which is 0 in the denominator. That's a 0 divided by 0, and I can actually get rid of that 0 divided by 0 by just canceling these out. Well, once I've done that, well, I can now evaluate this limit. So if I plug in x is 0 now, I get e to the 0 plus 1. That gives me 1 over 1 plus 1, or 1 over 2. So that's my limit at x equals 0. So what's happening at x equals 0? It really is actually a whole because I have factors that cancel. So I end up with a whole at x equals 0, and the y-coordinate of that whole is the limit, is going to be 1/2. So if I put on my y-axis, my whole is going to be right about there. Okay, I have an undefined value that cancels, so that is going to be a whole. So then what's happening as our endpoint behavior? And we're going to look at what's happening at negative infinity. So what I can do is I can plug in negative infinity in here, but to do this, it's much easier to do it into the simplified form. Because if I just plug it in as is, I get e to the negative infinity over e to the negative infinity. I can evaluate that, but it's much easier to use a simplified form since I've already dealt with the divide by zeros. Okay, so I can cancel them out. I've dealt with my restriction. So I can apply this limit on the simplified expression. So as x approaches negative infinity of 1 over e to the x plus 1, I can now evaluate this limit by just plugging in. I get e to the infinity plus 1. Negative infinity. E to the negative infinity equals 0. So what I end up with here is I get 1 over 0 plus 1. My limit is equal to 1. So what does that mean? It means that as I approach negative infinity, I end up with a horizontal asymptote at y equals 1. I then look at what's happening as I go to positive infinity. So same thing, I can, instead of dealing with the whole expression, I can use a simplified expression because I've already dealt with a restriction as a whole. And so I plug it into 1 over e to the x plus 1, the simplified version of this. And when I plug it in, I end up with infinity plus 1 in the denominator. That's equal to 0. So what does that mean then? As I go to the right, the limit as x goes to positive infinity, it's going to reach a horizontal asymptote as I go to the right. Okay, so what does this graph look like? Well, I'm just going to check to see if I have any zeros. So looking at my expression, I don't have any zeros because my numerator is equal to 1. The zero that I did have canceled out. So there are no zeros in this graph. So I have my horizontal asymptote towards negative infinity, my horizontal asymptote towards positive infinity. So to sketch this graph, it's going to look like this. I'm going to have an asymptote. It's going to go through the hole, and then it's going to follow the horizontal asymptote like this. Okay, so I'm going to have a graph that looks something like that. And we can establish this based on our limits to infinity or endpoint behavior, and we also ended up with local behavior to get the whole at x equals 0, y equals 1/2.